STROBE-X is a probe-class mission that will open a new window on the dynamic universe by bringing together high-throughput X-ray timing and spectroscopy at both the soft and hard X-ray bands, with continuous viewing wide-field monitor that will provide triggers to the pointed instruments and to the community.
The central instrument is the X-ray Concentrator Array, or XRCA, a high-throughput array of X-ray concentrator optics and detectors operating in the 0.2 to 12 keV band, with CCD-level spectral resolution, low background, and an order of magnitude more collecting area than NICER.
The other pointed instrument is the Large Area Detector, or LAD, which consists of panels of collimated large area silicon drift detectors. These provide coverage up to 30 keV, with an order of magnitude more collecting area than RXTE, and about 3 times RXTE spectral resolution.
STROBE-X carries a set of coded mask, wide field monitor, or WFM, cameras that continuously view about 1/3 of the sky at a time. These rapidly disseminate arc-minute localizations of transients. The WFM tracks the spectral state and variability properties of sources with a daily sensitivity of about 2 milligrad, with CCD quality spectral resolution.
STROBE-X is highly complementary to ESA's Athena mission, which primarily does X-ray imaging and high-resolution spectroscopy. STROBE-X does time-resolved X-ray spectroscopy over a huge dynamic range in brightness, extending in energy from 0.2 to 30 keV. STROBE-X will also have flexible scheduling, similar to SWIFT, allowing for monitoring of source states over time, but it will achieve next-level results by having the collecting area to allow full spectroscopic movies to be produced rather than just flux monitoring snapshots.
The technologies that we need to build the STROBE-X mission already exist. The primary instrument on STROBE-X, XRCA, is essentially a large NICER. The optics that we developed for NICER naturally extend to a larger size that we'll be using for STROBE-X, and likewise, the detectors are identical. In the case of the hard X-ray instruments, the LAD and the wide field monitor, ESA has undertaken a very long and extensive development program as part of LOFT that has greatly matured those concepts. In addition, we've designed the entire mission to be integratable. This is important because we need to integrate and build STROBE-X very quickly in order to meet the very aggressive schedule that NASA has put forth for the first probe missions.
STROBE-X will study black holes across all mass scales. It'll make high-confidence measurements of black hole spins, revealing how black holes form and grow. Crucially, STROBE-X will use a wide range of timing and spectroscopic techniques to understand the spins of black holes, allowing for a control on model systematics. This will, in turn, allow Athena to use reflection modeling with confidence for faint supermassive black holes, for which only reflection fitting works. STROBE-X will also give us the best view of accretion disks and how they drive outflows like jets and winds, leading to synergies with the upcoming next-generation Very Large Array.
STROBE-X's high throughput and flexible scheduling will enable it to contribute to a broad range of science beyond its core topics of black holes and multi-messenger astronomy. It will provide new probes of the neutron star equation of state and of thermonuclear fusion on the surfaces of neutron stars, both of which are core questions in the most recent nuclear physics decadal survey. Recently discovered quasi-periodic eruptions, which may represent extreme mass ratio inspirals, can be probed in great detail by STROBE-X monitoring. Meanwhile, in our astronomical backyard, X-ray spectroscopy of comets could tell us about molecular abundances in the early solar system.
Outside the time domain, STROBE-X's throughput will allow exploratory observations of integrated light spectra from extended sources like clusters of galaxies and supernova remnants. This can help establish global population properties and identify the most interesting targets for higher resolution follow-up. Spectroscopy of galaxy clusters, active galactic nuclei, and neutron stars also opens up new pathways to constrain dark matter models, including axion-like particles, which are well-motivated dark matter candidates.
An easily underestimated component of STROBE-X is the wide field monitor. This set of continuous viewing X-ray cameras represent a powerful new capability that will be a critical component of NASA's program in time domain and multi-messenger astrophysics. It will provide rapid positions to ground-based observers and study X-ray counterparts to gravitational wave events and gamma ray bursts. It will also provide long-term light curves for a large number of sources and can autonomously trigger deeper observations of new sources and rare states of known sources.
The wide field monitor can also be used to trigger automated slews of the pointed instruments onto events like supernova shock breakouts and extreme stellar flares, the kind that can affect planetary habitability. It will also produce unprecedented quality light curves of active galactic nuclei that can be compared with those from the Vera Rubin Observatory. Finally, integrating over time, With its good spectral resolution, the Wide Field Monitor will be able to search for Compton-thick AGN from their iron lines. These are the targets that are needed for megamaser cosmology projects.
The STROBE-X team is broad and inclusive, bringing together a great deal of experience building, operating, and analyzing data from X-ray missions, as well as fresh ideas from people new to X-ray astronomy. Our International Science Working Group has over 150 scientists spread throughout the United States and across the world. If you're interested in learning more, get in touch with any of our team members, check out our website, or follow us on social media.